This is chapter 5.4.4 of ZTransform, in which we study the block diagram realization of the difference equation. Given a difference equation, we can then transform it into the transfer function hz, relating the output yz over x of z. These are the coefficients of the numerator versus the coefficients of the denominator. Once we are in this form, we can break h of z into any parts that want. We can factorize it into any part we want. In this example, we have factorized this rational functions over with respect to two h1 and hz. Let h1 be y over v and let h2 be v over x. h1 is, in this example, is up to us, but in this example, we're only dealing with the numerator parts. While in the h2 of z, we're dealing with the denominator part. So once we have done that, you realize that in terms of polynomials, nothing have changed. h1 is this, h2 is this. When we multiply with the two of them together, we'll get h of z. Diagrammically, it looks like this. This is h1 of z and this is h2 of z. Now we of course can find what is v of z, which is v of z is simply x of z passing through h1 of z. So v of z is x of z, h1 of z. Y of z is vz times h2 of z. So we are actually manipulating the various transfer functions to represent yz with respect to v of z in this case. And therefore, y of n is simply v of n, a1 times y of n minus 1, a2 times y of n minus 2, and a3 times y of n minus 3. And similarly, if we are only focusing on vz and x of z in here, then vz transfer to inverse z transform to vn is this, xz is of course xn, z minus 1 xz is xn minus 1, z minus 2 xz is xn minus 2, and so on and so forth with their respective constant. This diagram also shows us an intuition. It is up to us to break and factor whatever h1 and h2 is. In infinite precision, it does not matter how we break this factorization. However, when you really deal with real system where you have to representing it in floating point or worse still in integers, then certain organizations of h1 and h2 is better than the other. But for this course, we're not so interested in it. And we'll leave to future courses for you to experience how finite precision effect will affect block diagrams organization. Now, what are the blocks diagrams that we are interested in? It's only 3 of them. When W is being amplified, we typically use a triangle and a value here, and the value k times Wn is the output. So it is an amplifier. When we want to delay a signal, we'll use z minus 1, then the output is Wn minus 1. If input is Wn, through a delay is Wn minus 1. And finally, we have a summer. So all these are being summed up, and therefore this is the output. So with these 3 block diagrams, we can actually realize any of the constant coefficients discrete time filters. Let's see an example in the next slide. In here, we have v of n, which is here, relating the output of v of n with respect to the input x of n. So b0 times x of n is b0 over here times x of, in this case we are in the z transform, so it's b0 times x of z to get v of z. We need to delay it by 1 sample. So here is x of n minus 1. So it's z minus 1 times x of z. And multiply by b1 to get vz. So if we want to redraw it, actually I can redraw this in the time domain representation. This is x of n, this is v of n, this is x of n minus 1, this is x of n minus 1 will be multiplied with b1. So this is the equation above, b1 times x of n minus 1. Then what about here? This is x of n minus 2 because it has seen 2 delay. So this is x of z, or this is x of n minus 1, x of n minus 2. Multiplied by b2, which is this b2 times x of n minus 2, then we sum again. So this vn is simply the sum of the past x of n minus 1, minus 2, minus 3 multiplied by these respective coefficients. That's all. Now, this vz is being passed through to get y of z, as in the previous diagram here. V of z is being passed through h2 of z, which is this. Right? So what is that? Then we are being passed through. So v of z now passed through y of z. So what is y of z? Y of z is of course y of n. So what is this? This is delay. So what is this guy? This is y of n minus 1. Y of n minus 1 times minus a1. You see? This is y of n minus 1 times minus a1 adding to vn. Then here is y of n minus 2 times minus a2 again. And here is y of n minus 3 times minus a3, adding all up to get y of n. So it is very easy to actually map the difference equation directly into something called the direct form 1 representation of the digital filter. So in the next page, we have given you h of z, and sometimes in the exams we ask you to draw the block diagram, and this is the df1 block diagram, and that's the simplest one that you will find. Okay, so just practice this and compare your results. Now I will briefly go through something called df1 versus df2. df1 filter looks like this. The B's are on the left hand side affecting the input. The A's are on the right hand side. And this is what we had done. In df2, it's different. We swap and we make the delay in the middle. So this representation actually will result in the same yn, but actually you'll realize that it saves the number of delay. Here you need 4 delays, while here you only need 2. The equation getting yn out from this equation is identical to this. It is just a different ordering. We have implemented y of a 1 over az before bz. That's the whole idea, and it saves on the delay. And it is nothing but factorization. It's h1 multiplied by h2 or h2 multiplied by h1. It is the same. But in this course, we're not interested in there are many other ways to organize this block diagram, but in this course we are only focusing on actually df1. With that, thank you very much.